Welcome. This is a really cool session. It's lead by the way, folks, we're not collecting. You know, there's no collecting here. You can sit up front. I won't say anything if you're. I will tell you if you're in the back though. People think we're collecting money if you're sitting up front. So this is lead by example. We've got three great participants here, speakers, who have done or doing projects that you have to hear about. Look at this, Steve. You actually listen to me. Damn. It's the first time I've ever had that happen.
No pressure, right?
No pressure, right.
Pressure.
So now that you're here, we'll make fun of you. No, I'm only kidding. One of the things in this about this industry and the fact that you're here is we're not new. We're 40 years old, but we're a new renewable technology, right, folks? So there's still a little sense of, geez, who's done it before?
Smile for the camera.
Nobody knew who I was. I was doing incognito. Yeah. The fact is that we've got opportunities now that we've never had before. We're going to have more opportunities, but the ticket is, if you're here to learn, this is where to do it. I happen to be chairman of IGSPA, so I'm going to give a 2-minute lesson or I guess a promotion. IGSPA does all the training for whether you're a design engineer, whether you're an installer, or whether you're a driller. So I would venture to say, if you're in this business, if you have a business, you should be in our business directory. If you're single and a single person, you want to learn more about this industry, become a member of IGSPA. We've got a table downstairs, and Sally will just take your information. Having said that, I want to introduce Indu Linu. Did I pronounce that right? You're not Italian, so it's kind of tough for me. She's from the University at Albany, and I know she's really busy, so I'm going to let her get on and tell her story. Thanks very much. And by the way, if anybody gets up and leaves, I will say something.
Thank you, Jack. No, I can't be Jack. I am Indu. I'm the energy officer at the University at Albany, and happy to be here and share some of the success stories with you guys. So we are in the process of creating a net zero carbon master plan, and for us, a decarbonized net zero carbon campus has 5 major components. The first one is, of course, very, very energy efficient buildings. So we just completed a deep audit, and we built energy models and figured out what we can do to reduce our buildings' carbon emissions as much as possible, which is in a financially responsible manner. So that's number one. The second one is to switch our heating, which is mostly fossil fuel based right now, to an electric source, again, as much as feasible. And to do that, we have to move away from the high temperature hot water systems and the steam systems that you typically see on a large campus to a low temperature hot water system. Once we have electrified as much as we can, the next step is for us to figure out how can we source that electricity from a renewable energy source that matches what we're using on campus on an hourly basis for the whole year, right? So that's our next step. So we're looking at both on-site projects as well as off-site projects for that. And the fourth component is data. We're building more complex systems. Our buildings are becoming like computers. Unless you collect data collection is cheap. Storage is cheaper. So collect, store, analyze, have diagnostics tools on top of it so that you're always being proactive with how you're maintaining your buildings. And the fifth one is, of course, making sure that your operators and your building occupants are educated. So this is a very preliminary view of the all of the efforts that will get us to that net zero carbon. Our goal is by 2044, which would be our 200th year of existence, to meet that target. But as you can see, about a third of the carbon emission savings are coming from decarbonizing our heating systems and moving to a low temperature hot water based thermal energy network. As a campus, we actually already have thermal energy networks. We actually have 2. One is the heating. one is the cooling. The problem with those systems is we're wasting energy on both sides of the equation. So during cooling, we're using electricity to reject heat to the atmosphere through our cooling towers. And during heating season, we're burning fossil fuels to generate electricity. So if you look at our heating and cooling load, you'll see that there are times when we have simultaneous heating and cooling loads because we have some year-round cooling conditions, and we have hot water needs even during summer. So those provide a really good opportunity for us to just recover heat through a heat recovery chiller and use that instead of wasting energy. But then you also have the heating load predominantly in the wintertime and cooling loads in the summertime. So that's where geothermal plays a critical role for us. So instead of wasting energy on both sides, the bore field, what that does for us is it takes all the heat that we're rejecting all summer long, puts it in the ground, which acts as a thermal energy storage, and then come winter, we're able to now pull that heat out of that bore field to provide heating to our campus. So we've started to look at areas on our campus where the green dots are. That's where we're looking for bore field. We've just completed 4 test wells on our campus, 2 with the U-bend loop, 2 with the RIGAN loop. We're analyzing those results as we speak. And we're also looking at which buildings are ready today, once we have this system in place, which buildings are ready today to get connected easily, and which buildings might require a little bit more work. And we're coming at these projects, this campus-wide decarbonization, central plant level decarbonization project, from a place of success. We already have 2 buildings on our campus that are fully electrified. One of them is the Liberty Terrace, which is a 500-bed apartment-style residential unit that has been open since 2012. So we have 12 years worth of data from this building, and this building uses a geothermal-based heat pump system for 100% of its heating and cooling with no backup fossil fuel on site. ETech is a 246,000 square feet lab building. Again, it uses like 60% outside air. It's very intensive. And again, that building is also fully electrified, heating, cooling, and domestic hot water heating from geothermal heat pump systems. And we've had great success with both these projects because we have all of the data, 12 years data on one, 4 years on another. We know that these buildings use less energy than comparable high-efficiency buildings on campus that rely on fossil fuel for heating, okay? So there's 40% reduction at Liberty Terrace, and might I add, that is with air conditioning. Not many of our dorms are air-conditioned, so we're providing an additional amenity, but still using less energy. ETech lab building, EUI of 65. Pretty impressive. Electrical capacity, that's another question when you're going to fully electrification. Can my electrical capacity support that increase? ETech at 246,000 square feet, the peak load is about 1.07 megawatt. Pretty good. We can get that with geothermal heat pumps. Air source heat pumps might be a little difficult, right? But with ground source, you can get that. Like I said, no on-site fossil fuel combustion, so there are health benefits from that. Just water savings, no cooling towers, no maintenance required for, don't have to worry about Legionnaire disease. So that's another big benefit. Like I mentioned, comfort. Air conditioning is now an extra that you get free from this system. So now I can air condition. In fact, I want to air condition, right? Because I want to use that as a resource for my heat. So perfect, I can air condition. Lower O&M cost, and really resiliency. Most of my asset, the bore field, is buried underground and it has a 50 to 100 year life. So I don't have to, and all of the other heat pump equipment is inside the building. I don't have any equipment outside that is subject to weather or other. So from a resiliency point, it works out. For our large scale, the campus-wide decarbonization, we're looking at thermal energy storage as another resiliency measure. Make heat or make cooling when the conditions are favorable, store it. So when, I have a power outage or other things happen or the price of electricity is too high, I can now pull from the thermal energy storage, and all I need is a smaller generator to run some pumps instead of running heat pumps. So again, it provides a lot of opportunity for us to diversify, have a more resilient, redundant system on campus. So I'll end with some of the lessons that we have learned through these 2 projects that we already have and the third major one that we're undergoing right now, do not forget about heater compression. I know we're in a region which is heating dominated, right? But with the heat pumps, when you're rejecting heat in the summertime, you're also rejecting that heat of compression. So do not forget that, because even Liberty Terrace, which is a residential building, we are rejecting more heat into the ground than we are extracting on an annual basis. Because we had data, we were able to show that. And now this summer, we're actually taking out the gas-fired domestic hot water heater in that building and putting it on the geothermal bore field so we can extract more heat. So do not forget that. Do not oversize your bore field. Understand your load conditions. Unlike traditional systems where you're looking at just your peak load and designing your system for that peak load, that's not how you design a geothermal system. You have to look at your annual loads and the balance between the loads to kind of figure out how much storage do I need? What is this bore field providing for me in this system, and design it for that. Because the problem that we have is when we oversize, it becomes super expensive, and then people are like, oh, it's not going to work for us. No, it is going to work if you design it properly. The other thing is designing what range of temperatures are you designing it for. Heat pump COP, if you look at the curves for the heat pump COP versus entering water temperature, it's super important to understand that, because your COP might suffer a tiny bit based on the entering water temperature, but maybe that would help you downsize your bore field. So you have to look at those pros and cons to figure out what is the right size for the system. Maximize pumping efficiency. Once you've got a really efficient heat pump system, heat pumps can be like, the COP can be 4 in heating compared to like 0.95 from a condensing boiler. So once you get to that high efficiency, pumping energy all of a sudden starts to become a pretty big part of the pie. So looking at your minimum flows, your bypass, making sure that you're not over pumping through the bore field, critically important. And as I've mentioned many times, data collection is critical. Collect as much data as you can and make sure that you find the time to analyze it so that you can take actions to make your building as efficient as possible. And with that, I will hand it over to Jim.
Morning, everybody. Indu is a tough act to follow, I know. I'll do my best.
I'm glad you're doing that.
Yeah. First would have been better, but it's all right. I lead the Department of Environmental Conservation's Energy and Decarbonization section. Our facilities are much, much smaller than SUNY's, obviously. We have somewhere over 200 conditioned buildings that range anywhere from small seasonal cabins through fish hatcheries. We even have a pheasant farm, education facilities, education camps, our campgrounds, of course, and our regional offices, maintenance centers, and that. One of the tasks of our group is to lead our department in electrifying our facilities, electrifying our vehicles, and at the same time providing lowering our energy use and providing a more healthy and safety environment for our employees. It's challenging. Resources are one of the biggest limits that we have, and one thing I'll be talking about today is kind of how we balance out some of those needs. Before I get into some specifics on some of our projects, I'll talk a little bit about some of the considerations that we really have to take into account whenever we look at a new project. Big thing is envelope. I heard a great quote yesterday that I like. It's, don't electrify waste. And it's absolutely right. So the first thing we look at is the envelope. What makes the best bang for the buck? Seal your building up, insulate it, replace the windows if they're that bad. Air seal, very important. Spend the time. That's not sexy, but it's important. Reduce your load, because electrifying is not inexpensive. It's very expensive. So if you invest the money in the envelope, you can greatly reduce the load that you need. I was also talking to Indu earlier, in some of our historic buildings that have old radiators. If you insulate the building, you might be able to satisfy the heating needs of that building with 130-degree water instead of 180-degree water. So you can save the historic characterizations or characteristics of the building. The type of system. I know this is a geothermal conference, but air source is often a very viable option. anything from a small VRF system for a caretaker's cabin. We start going up a little bit. We start getting into the new air-to-water systems, which work very, very well. And then eventually you work up into the geothermal systems. So you really have to evaluate what is the best bang for the buck, what has the best life cycle cost analysis result for your project. Are you going to go vertical bore field? Are you going to go horizontal slinky? Again, I mentioned air source, open loop, closed loop. All consideration has to be taken into account very, very early on. And the climate. As Indu mentioned, you're using the ground as a battery. You go up in the far north and you're going to find out that your heating loads are drastically greater than your cooling loads. If you don't know what the subsurface strata is of the area and you predominantly pull heat out of the building without rejecting anything back into summer, you could lose the efficiency of your well. So in a lot of cases, we will actually downsize the geothermal system to handle the cooling loads and use a hybrid system for the peaking loads that I'll get to for in a moment. Distributed or heat pump. Distributed or central systems. Predominantly, we've been using central systems, and I still do prefer those actually, but now we're starting to experiment with distributed water source heat pumps. There are benefits and detriments to both. Another important design consideration. And I touched on fully electric or hybrid. EO22 is often misunderstood to say that you have to have fully electric buildings. You don't. If you can, it's great. That is the overall target. But in a lot of cases, it just doesn't make sense, even from a financial standpoint. I would rather have 3 buildings at 60% capacity electric rather than 2 buildings at 100% capacity. So when resources are a limitation, you have to look at that. And there's other reasons for hybrid systems as well. Emergency backup. If you have an existing facility that is currently working on a propane modulating boiler system and you have a generator set to design for that particular load, now you're going to electrify. If you use a hybrid system, you can use that existing fossil fuel system to handle the emergency needs of the building and not have to replace that existing generator that you already have. So it all comes down to the best bang for the buck, and in our case, to best leverage the finances that you have available to you. Right sizing. This is very important. I touched on this before. Often we find that an electrified system designed for 60% of the capacity will actually handle about 90% of your needs. So the cost of the bore fields, the cost of the trenching and the systems are so expensive, it might kill the economics of the project, where if you right size the systems and say, okay, 10% of the time I'm going to have to use hydraulic, or I'm going to have to use a ModCon system, that's better than not doing the project at all because you couldn't afford it. I'll go into some of the projects that we have. These are the geothermal projects that we currently have either completed or in design. This is just ground coupled. We have numerous air source systems that aren't on here. Various types. We have bore field, we have horizontal loop, and we even have one open system that I'll talk about in a moment. Five Rivers Environmental Education Center. This was actually on the bus tour yesterday. This is a LEED Platinum building. It's actually 2 buildings that are all ground coupled. That one is 100% electric. We also have renewables on the building that provide not all, but the majority of the electrical needs of the building. That's working extremely well. Godfrey Point Science Shop, a very small project. Many of you designers will kind of recognize the schematic and who did that. This is a hybrid system. We have a propane ModCon for backup and peaking. That is a horizontal loop system working very, very well. Mount Loretto, similar to the Godfrey Point job, but we learned an important lesson on this. They weren't careful enough when they backfilled the system, and out of 4 loops, one of them got lost. One of them was leaking. Luckily, it was over-designed enough that we were able to shut down the one loop and operate on 3, which is still working very well. But it's just a lesson that even though HDPE is pretty indestructible, the joints aren't. So you have to be very careful with that. New Paltz Regional Office Building. This is one of our first that we did. This is fully electric. lesson learned there is pay close attention to the heat pumps that you get. When they first did it back in 2006, the engineer took an OR equal. It turned out not to be an OR equal, and we've recently replaced those. So that's a lesson there. Really pay close attention to what you're getting up front when you start. Stony Hill Environmental Education Center, a very small education building, which could have been LEED Silver, but it was so small we didn't want to go through the expense of doing that. Ground coupled, water to air, again, working very well. Van Hornsville, this is a really cool project. One of our engineers was putting a domestic water well in for a hatchery manager's residence and hit a 40 GPM artesian well. So he used that water and ran it through a double heat exchanger, heating and cooling the building for free, and taking that excess water and coupling that with the existing water system of the hatchery, helping to raise the fish. So I love this project. Planned projects. All the projects I'm going to talk about, these all include a very heavy photovoltaic contribution. Some of these are going to be net zero, but that wasn't really the goal. If we can do it, great. If we couldn't, again, it comes down to resources. Cortland Regional Office, this is an interesting project. I've already done a lot of deep energy retrofits on the building itself, so we wanted to convert over from natural gas over to geothermal. We are doing that, even though this will be a hybrid system. We're going to maintain the natural gas for peaking and for backup. The original well field was going to be down on the bottom right-hand side of the screen, and for setbacks and other subsurface conditions, that didn't prove to be that viable. So we moved it up closer to see where the red is, and there we're dropping the number of wells down and going 600 foot on that because of other space constraints and subsurface utilities that we have. That right now is in final design stages. Northville Regional Office, very similar to Cortland. It's smaller, but this one did not have any envelope retrofit, so that one was in pretty bad physical shape, so we're doing a lot of work on that, improving the envelope. Like Indu said, we're moving the thermal envelope from the ceiling to the attic so we can put our DOAS system up in the attic and keep all of our mechanicals up inside a conditioned space. This one here is going to be covered in photovoltaics, and that is going to take this building projected to be net zero, which is a 1970s building, so we're proud of that. Raybrook Regional Office, another very interesting project. This is up north. We have a large distribution or large difference between the heating and cooling loads. So this is the one I said we've designed the geothermal system for the cooling loads of the building. That we're going to balance that out towards heating for the shoulder seasons, and then during the deep cold, we're going to be relying on our existing district biomass system that we have up there for the primary heat during the winter time. You can see we already have our test bore in, which actually wasn't as great as we thought it would turn out to be, but we didn't have to add any wells. Pre-design, Cleveland Law Enforcement Academy. That was an old middle school that we are converting into a law enforcement academy. That one is going to be fully GEO, again with a hybrid backup. But I don't expect that backup to be used too much, but it is going to be there that we can use for peaking and to balance out our loads. Rhinestone Woods Education Center out in Depew. We have an existing 5,000 square foot education center there now, and we're going to be more than doubling the size. And we're getting rid of the mod cons there, and we're going to go full geothermal. Solar's going to be a problem there because it's called Rhinestone Woods for a reason. But anyway, that's my presentation. Thank you.
Hi, I'm Lachlan, Squair, Associate Vice President Facilities at SUNY Oneonta. So I don't know if you've heard of us. We're one of the SUNY campuses in Oneonta, New York. We're about 2.4 million gross square foot of floor space, about 5,300 students, 47 major buildings. We have a hybrid thermal energy network system, so we supply a lot of buildings with steam, which is then converted into hot water for heating. We also have a medium temperature hot water network as well. So the steam is the older sort of legacy network. And we do have some small number of buildings that are on natural gas boilers. In general, our steam and medium temperature hot water networks are in excellent condition. We're lucky to have tunnels between buildings. So there's a lot of advantages with that energy transportation infrastructure. Our central heating plant is natural gas. Primarily we burn natural gas, and I'll get into some of the regional energy issues. But we would do a fuel, so we switch over to fuel oil on way too many occasions. Our central plant it's in great shape as well too, and it's estimated to have another 35 years of life. So we started our clean energy master plan in about 2018. We finished in 2020, and we were really looking for a roadmap to decarbonization by 2045. What pushed us into this is we have some specific regional energy issues, which I'll get to, and some limitations with our utility. And part of it was we wanted to utilize our existing energy infrastructure until it was at end of life. So we realized we had an asset there that we should use until it's worn out. But we also, through the process, we stopped looking at buildings as standalone buildings in the middle of a city. And we came to this realization that buildings are components of a larger system. So if you're electrifying a building, you don't necessarily need to do everything at that building level, as long as you're looking holistically across the whole campus. We really wanted to keep our options open because we don't know what future technology is coming. These are very long-term clean energy master plans, 2045, 2050. That's quite a few years away. We don't know what future technology is coming, whether it's hydrogen or some other technology. So whatever strategy we wanted to take, we didn't want to paint ourselves into a corner by committing to something that would preclude the use of other technology. And we're a university campus, and capital expenditure on a university campus should really be driven by academic needs. So we have all sorts of responsibilities for stewardship, decarbonization, stewardship, reduction of deferred maintenance, but we are an academic institution. Our mission is education. So that's a big part of capital investment. So somehow we have to integrate what we do here with decarbonization, with critical maintenance, and as well as with our facilities master plan, which is driven primarily by academic needs. So I mentioned our regional energy issues. There's a gas line spur that supplies Oneonta. It's old. There's some issues with deterioration of that pipeline. It's undersized. Actually, the supply of gas constrains Oneonta somewhat. We're an interruptible customer, so we're very regularly pushed off gas with an hour's notice, and we have to burn fuel oil, which costs us a lot. So this is on an average winter. It's an additional $120,000 for being pushed off gas onto fuel oil. This winter was pretty bad. I think we're up to $400,000 additional expenses for burning fuel oil. So some of this early on consideration of our particular regional energy issues sort of pushed us into doing our clean energy master plan because we wanted to try to reduce our dependence on natural gas. So, so at a high level, our current distribution network is steam or medium temperature hot water. That goes out at 275 degrees. The vision is that we transform that energy transportation into low temperature hot water distribution. We put in thermal storage, and then that puts us in a position where we have a network of low temperature hot water. We can plug in other technologies as we need to. We currently use fossil fuel boilers for baseload and peaking, and then our plan is to use heat pumps ultimately for baseload, and some fossil fuel or renewable fuel or biofuels for peaking and backup. We currently get all our electricity from the utility, but our plan includes construction of on-site solar, and we're just about to start on construction of 1.5 megawatts of on-campus solar, as well as solar PPAs and purchase of RECs, etc. So this is not as good a graph as Indu's got much better graphs than me. But there you can sort of see the plan here for reduction. In the short term, we do deep energy retrofits. We look to do things like envelope work and improve energy efficiency. We want to get off the steam distribution first. because of the losses involved on there, we can get a lot of energy savings by transitioning from steam energy distribution to low temp hot water. We're going to purchase renewables. We're going to build renewables. And as all, we also have another mission within our campus constituents of engagement, energy efficiency, and saving energy that way. Longer term, what we're going to do is integrate with our facilities master plan, and either have a low carbon energy supply through energy production on campus or purchase. So just to sort of summarize our clean energy master plan, our plan is to build distributed geothermal arrays. So as we do deep energy retrofits on buildings, we're going to build a geothermal array by that building, and maybe that'll be oversized or slightly undersized depending on the real estate that's available. We're going to institute energy conservation measures, have on-site and off-site solar, build thermal storage, convert our steam and medium temperature hot water to low temperature hot water distribution. And then we're going to establish a new low temperature hot water distribution network. So then the geothermal fields that are currently or in the near future are going to stand alone are going to be networked. So they'll be interlinked. So there'll be an ability to sort of operate a larger network of a fossil-fired central plant, but also a number of nodes of geothermal energy production. So our central plant is in excellent condition. It's probably got 35 years of life left on it. We're probably going to continue using that. And I'll get to that as we get into this a little bit. But the distribution pipe's in good shape, as is the plant. There's no reason we can't do fossil fuel peaking until the end of the life. So this is an interesting graph. When we got into our clean energy master plan, the estimate was that we would probably need 1,000 wells or so to fully electrify the campus using geothermal. There just isn't. We're congested. Underground utilities, we're very congested. There just isn't enough real estate for that. And through the process, we came to realize that if we were to base load, we could cover our base load with, say, 500 or 600 wells, and that might get us an 85% reduction in Scope 1 and 2 greenhouse gas emissions. So a couple of sample projects. Alumni Hall was finished in 2023. That was a LEED Platinum project. We did 39 wells at 499.999 feet deep. There's mostly gray shale down to 500 feet. And you can see the thermal conductivity and diffusivity for anyone who's a geothermal nerd. I'm sure there are people here. That building is fully on ground source heat pumps, both base and peak. We left the central heating plant steam into the building. It's not connected to the building systems in any way. But as we move along, we may possibly reconnect that to the central plant for some purposes. We didn't want to completely cut that tie. Our Netzer Hall renovation is a larger project that starts this fall. We're doing 65 wells at 600 feet deep. We did a test well December last year. We were looking for 750 feet, but we went down to about 660, and then we hit refusal. There was some concern at the time that we might encounter that depth. We might encounter oil or gas, but we didn't have any real problems with the test well that way. And the two buildings are not too far apart, and there were similar sort of conductivity and diffusivity figures. So the difference is, though, on the second project, we're not going to have the building fully peak and base on geothermal. Firstly, there were space limitations with how much wells we could actually fit in the parking lot. And then we've just come to this realization there's a lot of cost in doing additional wells. When you already have the central heating plant connected to the building, it's in excellent condition. There's a huge capital advantage to reducing the number of wells to more of a base load, or perhaps the cooling set to match the cooling. So this is the real kicker, though, because through our clean energy master plan, we looked at what the additional electrical load on our campus would be given certain scenarios. So our electric peak is in September when the students come back. That's usually 4 or 5 megawatts. We own our substation, and as we move towards electrification, that peak is going to shift. So you can see from these graphs here, if we go for a centralized ground source heat pump, air source heat pump, the electric peak's significantly higher. We're looking at electric peaks in the 18 megawatt range, 12 megawatts, which is more electrical energy than our underground distribution network on campus can handle, and it's also more electrical energy than our utility can supply us. So if you look at some of these scenarios like natural gas peak, that's a 6 megawatt peak in February versus our 5 or 6 megawatt peak in September, which we currently have. So there is a real consideration about sort of a proliferation of electrification that the grid won't be able to handle it. And if you're on a campus, you have your own internal utility distribution network, which may not have enough capacity. So we're handling that. We're about to replace our underground electrical cabling. We currently distribute at 4,800 volts. So we're pulling a higher rated cabling in anticipation of replacing the substation in 10 years when the load grows, so that we can go up to 11 or 12 kilovolt distribution. Yeah. So, but this is the real limitation that I think people have to be very, very conscious of, is that there may not be the capacity to get power to, if you're looking at a large facility like a campus with 2.4 million square feet, the utility may not have enough capacity to get the power there, and you might not be able to distribute that across the campus. So, but our big takeaway too is really that each of these projects, there's no golden solution to every project. You have to look at the real specifics of the project. How much room have you got? What are the heating loads, cooling loads? What is the electrical distribution system? Can you get enough power to that building? What's going to happen when you do this building and this building and this building? So it's a real critical thinking exercise.
Thanks.
Thank you.
Thank you. Kind of time. Well, thank you. They were great presentations. I will say a couple of things. Only because I've been doing this, and by the way, I have the same life expectancy as your central plant, about 35 more years. The term wells drives me crazy unless it's an open loop system. And those of you who know me, it's their bore fields or their ground loops, or, just so I've been in so many arguments with city planners and things like that. We can't do wells. And I'm thinking, they're not wells, they're boreholes. So you just heard 3 really great presentations. In fact, I would say that they were probably some of the best presentations I've heard in 40 years. Indu, I'm glad I wasn't following you, because that was spectacular. We're going to open it up to questions now, and I know some people probably have questions of our 3 panelists. They're the experts doing it now. So anybody have a question? Yes, we'll start up here. John, you got it?
I got it.
I was going with you first, but
the man with the mic gets to decide, I guess. Sarah Collado with Siemens. A question for James. I wondered about the state procurement model. Because one of the things that we're hearing with this complexity, and that every solution needs to be really considering a lot of different factors, and it seems like the typical design, bid, build model often doesn't serve. I mean, certainly in a complex campus environment, it doesn't. Your projects are more individual buildings, but I'm curious to know if DEC is paving any ground for the state to adopt more of a design build type procurement methodology.
We have not been exploring design build ourselves. We really don't have that avenue open to us at the moment. We do for certain elements, but not for building electrification. The projects that we're doing are typically designed, then bid and constructed as a standard large contract would go. Small installations we're doing, a lot of them we're doing ourselves internally, where we would use possibly procurement contracts or other mechanisms to buy the equipment ourselves and install them. But as far as design build, that on this element, we haven't been doing. Please.
SUNY has been seriously looking into other options because we realize that one, we don't have enough capital to go at the speed that we need to meet our targets. Two, these kind of systems inherently have some risk associated with it, which is not our expertise, right? As Lachlan mentioned, we're here to educate, not to run infrastructure projects. So we realize that there is some limitations, both technical and financial, that the private market can help us with. So SUNY recently issued an RFI, and we got a very healthy response, trying to evaluate all different options, whether it's design build, whether it's design build own operate type models, or whether it's utility as a service, PPA. So we're trying to analyze all different options to see what is feasible, what is allowed right now in the state regulations, what we need to advocate for as changes so that we might be able to access what the private market has to offer.
We're doing our underground electrical distribution replacement as design build. And it's a learning experience. I'm not sure if the state is quite ready to sort of get its head around that process. It's not going too badly for a first time for our agencies.
That I gotta say that I've been doing this, like I said, a long time. What I see now from larger companies, we have companies coming in that want to design, build, own, which takes the onus off of, as Indu said, takes the onus off the end user, but it also keeps the hook in whoever designed it. Those of you that do contracts, you know, if you design, build, and then walk away, you don't have any onus. So next question, right. The young man from Pratt will be next.
State next.
Lee McKean, DEC. I guess I was just wondering about, with so many different parameters to consider, I completely lost sight of the fact of what you just said, that you're an academic institution. Because I was like, yeah, no, just do this, like go whole hog, right? But so in terms of budget concerns and, you talked about replacing the underground conductors and stuff. And I guess I'm just wondering, how does that process work? How do you fit all these pieces together? Is there a standard procedure for that?
We drink a lot.
Oh, okay.
You mean, are you talking about the procedure in-house to achieve that, like procurement procedure?
So one of the critical things is master planning.
Yeah.
And I've said this, maybe some of you have heard this before, but I love doing jigsaw puzzle, but I like to have the final image. The master plan does that for you. So once you know what that future state is going to look like, every time you have an opportunity, because a program is going, you need to renovate this building. Because the system failed, you need to replace it. Whatever the case may be, now as you're thinking about the solution, you know how that fits in or doesn't with that final picture, right? So you can now start to maximize and leverage whatever funding you're getting and utilize every opportunity to move in the right direction.
Yeah, and I wish there was an easy answer because it's extremely difficult. I guess that's why we have our jobs. But but like Indu said, you have to have a facilities master plan. You have a good sense of where the institution needs to go, 10-year goals, and then the clean energy master plan is really the kit of parts. So when it's the next step is to do this deep energy retrofit the next step is to do this renovation of this building for programmatic reasons and critical maintenance. Then you can start to fold in some of the elements. But it is very difficult. There's not unlimited capital, and you're constantly making decisions and that's part of what we're getting to here with maybe sizing geothermal for base load, because that's a lot of savings in capital money that can go back into other critical maintenance needs, that can go back into programmatic improvements, can go back to other energy conservation projects. So it's a constant, it's also really reiterative. So you have a facilities master plan. We're almost planning on a 2-weekly basis with all the conflicting priorities and new needs that come up.
Yeah. The new needs are a real issue. You can plan all you want, then something major happens, and all of a sudden you have to regroup and take both your staffing resources and your financial resources and redirect it to another one. So, and then also with the New York State, we are on a very short budget leash, and it's hard planning 5 years, 10 years down the road what you can do, because you honestly don't know what you're going to have next year.
I don't think the budget has passed, has it?
Not yet.
Is the budget passed? We don't know what we're doing this year. So, but it's very hand to mouth, because just the capital allocations that come out of the budget even can affect the strategy they're working to adopt over the next 12 months or 2 years. So it's
The other thing that I will say to you and everybody in this room is, with ground source of geothermal becoming very, very in vogue, we're going to have people that are pretenders, okay? And I've said this before. Make sure that if you're doing a major project like these three of our folks here, that you get a resume, okay? It didn't just, I just bought a magnetic sign that says I'm a geothermal expert, because one of my jobs is to make sure the technology, the integrity of the technology is kept up and the end user is kept whole. So just for everybody's, just so you know, a ground loop takes 2 years to fail, 2 years. So by that time, Harry Schwartz, who just bought that magnetic sign, he's in another business, and you're stuck with it. So that's why I really do like having those people own the project, because that gives you some, they're like, if you're a Siemens, if you're a ESCO, you've got to produce, because if you don't produce, you don't get paid. So, and that actually helps your budget, because there is no outlay of cash, so to speak. You're paying a monthly fee, so and they're taking care of it, so it helps your maintenance costs for a geothermal system go down 40%. A ground loop, according to some of the studies we've done, just for James, I don't know whether it's Lachlan or James, a ground loop geothermal system will reduce peak load by 0.55 kW over a conventional system. So what everybody doesn't realize is 40% of all the primary energy used in the United States is used in buildings. It's not cars, it's not trucks, it's buildings. So the stuff that we're talking about here is really critical if we really want to get to energy security and independence. I think the gentleman from Pratt is next back there with the good-looking vest on.
So you're going to say good-looking guy.
I wasn't going to go that far.
Thanks, Jack. So, Lachlan, just a quick question. Your last graph with your bars showing the peak, your ambient loop looked the best. Is that a correct?
I think that
Well, you said
it was not the best. Is really
right.
Ground source heat
to get the best without fossil fuel.
Correct, but we don't favor the ambient loop, because we felt through our clean energy master plan that might cut us off from other sources of energy production. That was just a choice that we made, that we would go down that avenue of low temp hot water distribution. But it's a better option.
So you're confusing me. Which
ambient loop.
Which graph are you going down here?
I'm sorry.
Which bar are you following?
We're doing the centralized ground source heat pump, air source heat pump.
The second one.
Yeah, the second.
The second one.
So 1B.
Yep. Ambient loop is slightly more, because it would be a lot less centralized. So you might have heat pumps in every building in an ambient loop on the campus. Right. But we tossed that one around, and we sort of are concerned through the whole process. We're concerned about we don't know about other technology that's going to come along. And if we're just distributing water 180 degrees, 175 degrees, whatever it's going to be, there might be other technologies that could plug into that network.
So if you'll allow me, you mentioned open loop, but then either I dozed off or
Open loop?
Didn't you mention an open loop system?
Do an open loop, but that was not by design, but by the fact that you had an artesian well, right?
Correct. Yeah, the open loop we did was it was blind luck. We drilled a domestic well and hit an artesian.
Oh, okay. Right,
so we just utilized that for the free cooling and heating of the building, and then added that to the fish production.
I think we're going to do something similar if we hit gas.
Yeah. I'll tell you what, open loop, the problem with open loops is the fact that water quality has a real impact on the heat pump itself. St. Patrick's Cathedral is 12 standing column wells, 1,200 feet deep. Well, they've got to backflow those heat pumps once a month. So maintenance gets pretty heavy. So unless you have, like you said, James, unless you have something that you hit and you can use it, and its keyword is free, open loops are not very well received in most places.
Yeah, and we had to drastically oversize the heat exchanger to handle the water flow and the water quality issues as well.
Do you pump it back into the ground?
No, it goes down. It actually flows
It
down.
runs up.
It's piped back to the fish rearing process.
Yeah.
By the way, that's pretty cool.
It really is.
Hi, Ron Kamen, Earth Fund Energy Consulting. So last session we were talking about the direct pay IRA refund. Just wonder if you guys did any of that and what your experiences were.
You want to bite that one?
Because yours is too old. So
Yeah, the two
the
projects.
completed ones
Two
you're happy.
projects are old. The new ones, SUNY has started to look at it. We have one project, SUNY-wide, that is under review right now. So depending on how that goes and how cumbersome that process is, we might.
Yeah, we've also supplied a whole bunch of information to SUNY about the IRA direct pay, but I'm not sure where that is at the moment, if it's going to amount to something.
The other, sorry.
Oh, sorry, go ahead.
The only other point I want to mention is even if the money comes back, it might not come back to the university. It'll go to the state of New York.
Right.
That is the current problem right now. New York State has one tax-exempt ID number, or I'm sorry, tax number. So right now, my agency and others are working on mechanisms to either leverage the direct pay or the IRA itself in order to get that money back either to the contractor or right to the agency that expelled the money. Right now, it's still under debate, so we've not done it yet.
It has to go back to the end user of whoever owns that property, right? That's the way it goes. If you're on PJM territory, they have a renewable energy credits that can be bought. In Pennsylvania, it's $700 a ton. In Maryland, it's $3,300 a ton. I just consulted to a school that did a project in 2019, and they just got $240,000 in their hand for the energy credits. So if you're working in PJM, be aware of that, of anything from 2018 on.
I do want to mention, so ETAC, which was online in 2021, right? When we looked at a localized chiller boiler system compared to this ground source heat pump system, we did a life cycle cost analysis. And even though the bore field itself was a $1.9 million, so upfront capital cost, the life cycle, when you looked at the life cycle cost, it was $1 million cheaper for us to go with the geothermal heat pump system. And this was without any rebates or incentive. This was without any social cost of carbon. So financially, sometimes it might still make sense if you look at the whole life cycle cost.
Mm-hmm.
Over 20 years.
Over 20, 25 years.
Yeah.
Yeah, we've had the same issue looking at geothermal versus VRF, where VRF has a lower upfront cost, but there's so many negatives of that with the circulating the new refrigerants through the building and the peak kW demand on the building. You put all that together, look into the life cycle cost of it, and you find out that even though geothermal has a much higher upfront cost overall of the life of the system, it's typically much more effective.
Yes, sir. Here he comes.
Say your name. Thank you. So I see. So you central ground source heat pumps. So you're using heat pump chillers, correct? Okay. And then what refrigerants are you using?
Changing. It's changing.
Change it.
It's whatever you put it in.
You change it.
What is it this week?
Now, when you put it in
2021, that's a 410A system.
10A.
That's already being phased out.
Right.
So for the central plant project, we're looking at both the low carbon, low GWP refrigerant, synthetic refrigerant, but also natural refrigerants. The Liberty Terrace domestic hot water project that I mentioned that's happening this summer is going to be a CO2 heat pump. At the central plant, we're looking at CO2, but mostly ammonia and some of the synthetic low GWP.
What's interesting is, we recently did a trip to Denmark, and there's a lot of use of ammonia refrigerants. They don't really like the toxic flammable refrigerants that are being developed here.
So my mentor did ammonia, and he said it's horrible, right? And I'm just telling you, the guy, God rest his soul, but he says you get burned, the metal gets corroded, the guys lost their eyeballs, right? So, but what about why can't we go CO2? I mean, what's the real downsides to CO2?
There's a lot of equipment becoming available now, but size,
That is the problem. It wasn't the equipment wasn't available, and right now it's still not as available as say normal ground source stuff. Yeah, but it is available.
Right, because to me, these refrigerants are driving me out of my mind, and I mean, you're saying you put a system in 21. That's 4 years ago, and now you have to change. You have to change the refrigerant.
We don't have to change.
You're just out. Yeah, okay, and yeah. So to me, after these 2 days, I'm like, I want CO2.
You don't have to, if it's already installed, you don't have to change it.
No, true.
Okay.
Right. But
and if you're not buying, like right now, that's even up in the air, isn't it? About the ban. I thought I heard that was.
I thought DEC's regulation is in effect January 9th, 2020.
Yeah, I think the president's trying to put a moratorium on the ban.
Okay.
Right. But yeah.
But
okay.
that's going to be in the equipment. That's going to be by the manufacturer. They'll deal with that. Anyone else? I would say to you that if you can, this conference has been great, but this has been 3 of the best presentations I've seen yet. And the whole thing is what works, what's practical. I've never been one to say, geez, you got to go all geothermal. You got to do what works, because what's bad for us in our technology is somebody just goes all geothermal and it doesn't work, or it's too expensive, or it doesn't do us any good. Okay. So listen to what they've said, because they've done it already. And the other thing is, if you're not trained, once again, I'm chairman of IGSPA, you should. What I'm saying to utilities and to large campuses and even schools, do not hire anyone that's not trained. Do not hire anyone that doesn't have a resume. I'm not talking residential now, and even residential, but I'm talking commercial, institutional. And right now, think about this. For those of you wanting to get into this that are big companies, there's 131,000 pre-K schools in the United States. 52,000 of them have failing HVAC systems. The average age of a school in New York, I live in Philly, it's 71 years old. Average age here is 62 years old. Average age across the United States is 50. So we're putting our kids in schools that I could have gone to grade school in, which is really stupid. But I really appreciate your attendance and like I said, if you can, talk to the 3 of them, because once again, this has been the best presentation that actually hit it on the nose, that wasn't bad one way or the other.